So after looking at relative mass, we can finally introduce this idea of the mole. And when I say the mole, I'm not talking about the furry little blind rodent that burrows under the ground. I'm talking about the chemistry term which is foundational to the rest of the year. So from last day, before we move on, what I need you to remember is that there's two different mass terms that we've talked about. One so far is relative mass, and for something to be relative, it means that we're comparing something. So we're comparing a mass of one thing to something of another. When we look at the relative mass of all the elements, they are based on or were compared to 1/12 the mass of a carbon 12 atom. The reason that they selected that was to give it a value of 1.0, which we know makes the math easier to calculate how many times larger is this thing than the other. Remember that when we're measuring the mass of an atom, or a molecule, it has units of atomic mass units, or AMUs. Now, if we look at a molecular mass, that's the mass of a molecule, which is composed of different elements, multiples of different elements. So we end up having to consider the types of elements that it's made out of and how many of each element there are. Because again, this is an individual unit and an atomic or molecular size, it has units of atomic mass units, or AMUs. Now, the mole comes from that idea because although it's nice to have an AMU, that doesn't actually mean anything. You can't put an atom on a scale or a molecule on a scale and weigh it. It's not like a gram that you can actually count or see. So the mole is a convenient way of counting a very, very large number of particles that are very, very small, such as atoms or molecules. And we relate them using lots of different measures, but for example, using their mass. Because atoms are so very, 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 very small, they are impossible to count or weigh individually. So when we want to weigh them at a macroscopic level, that's at a large scale level, we have to have a large quantity of them that we can agree to weigh. And that's really what the mole is. So just to give you an idea of the perspective of the mole, how big that actually is, if we were to stuff a house with a standard chocolate chip, because you said, say you won the lottery and you won a mole of chocolate chips, you would go and you would fill your entire house, and that would take up about 1 billion of your chocolate chips. And you'd be like, great, I'm almost there. No, nowhere near a mole. So now if you went to a large city, say Vancouver, and you filled all the houses in the entire city with chocolate chips, you still wouldn't even have close to a mole. That would only be 10 to the 15. That's a million billions. So if you then went to an even bigger level, say you went to the level of the earth and you covered the entire earth 3 meters deep with chocolate chips, that would take about 10 to the 22. That's a million, million, billions, and times 10. 10 to the 22 chocolate chips. It's 1 and 21 zeros. Still not a mole. It would take you 60 Earths covered 3 meters deep in chocolate chips in order to take a mole of chocolate chips. So that should give you a perspective of just how small the atom or a molecule really is. So the mole is the name given to a very large quantity of atoms or any other objects. It's kind of akin to or the same as having a very, very large dozen. But really, the only useful thing to use a mole for is the atom or the molecule because they're so small that it takes us to a level which is useful. But the quantity equals any mole is 6.02 times 10 to the 23. If I was to write that out, that would be 6022 and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 zeros. That is a mole. So like I said, it's a big dozen. So you could have a mole of tin cans or Skittles or paper clips or thumbtacks, anythings. It's just a collection of objects. And we give this name or this number a special name called Avogadro's number. By definition, a mole is the number of atoms of carbon-12, or 6.02 times 10 to the 23 atoms of carbon-12 in 12 grams. So when we look at 12 grams of carbon-12, it contains 1 mole of carbon-12, or 6.022 times 10 to the 23 carbon-12 atoms. Since there's a connection here between atomic mass of the elements on the periodic table, and we know they're all compared to carbon-12, then the mole is also related to carbon-12, and there's a relationship between the atomic mass of any element and the number of moles of that element. And here's the relationship. If you take an atomic mass of an element and you express that in grams, then you have 1 mole of the element present. So, in 1 mole of an element, you have the same number of atoms as any other element, 6.022 times 10 to the 23. 1 mole of helium contains the same number of atoms as 1 mole of gold or silver or lead or any other element, except the 7. Oh, bromine and iodine. Which, when they're elements, are diatomic. So they're found as 2s. So when you have those particular molecules, the diatomic molecules of elements, you end up having twice as many atoms in 1 mole of the molecule of the element. So we've talked about molecular mass. It's the mass of a molecule, and it's calculated by considering, again, the number of types of the elements it's made of, and it has units of atomic mass units. And we can now bring up a new term, which is called a molar mass, the mass of 1 mole of a molecule or atom. And that's calculated by, again, considering the types of elements that are in it and the number of each type. The same thing. The difference here is that it does not have units of atomic mass units. It has units of grams per mole. You can write it as grams/mole, but really what I want you to know is that it's a unitary rate. So we have grams over moles. So we've got something that we can flip. Next day, we're going to be looking at calculations, and they can all be done by using unit analysis. All you need are the derived units. And there's 2 that we know so far. One is Avogadro's number, which says that there's 6.02 times 10 to the 23 objects. So that could be an atom or a molecule or a Skittle. You can tell I like Skittles. Per 1 mole. And we also have the molar mass, which is in grams per, again, 1 mole. So remember, the 1 is going to go in front of the mole next day when we set up our calculations. Although you can perform all of these calculations using unit analysis, and I will try very hard to push you to giving it a try, I will also give you a backup method that you can use, which is using formulas, but I will require that you memorize those. So I really encourage you to use the unit analysis because it just is a procedure. You just see how you flip it back and forth. But we'll work through that part of the game next day.